we continue our discussion on the nearest neighbor classification techniques. So, one problem we discussed in our last lecture was the problem of computational complexity. So, the reason that computational complexity is high is that, so you have in the k nearest neighbor, what you do, you have a training set, a list of instances, let me denote by these blue dots, and then whose class level I know, then I have a new point, I call the query point, and what I do, I find the k, some value of k nearest neighbor of this query point, and then I look at the class of this query point of the neighbors, the majority class, we put it into that, classify the query into that class. So, for every query point we want to classify, what we have to do is to first find out its distance to all the training points, and then so first step is second step is sorry, not the instances, sort the distances in ascending order, and using the sorted distances find k nearest neighbors, okay, and then take the put. So, this step as well as this step is computationally complex. So, what we did, we used two strategies. One is to reduce the number of training instances. So, reduce your number of training instances. So, again one possible way of doing that was by something called a condensed nearest neighbor, where we find a sort of minimum set of examples and replace the training set by this subset, we preserve the class boundary. Okay. So, we call it a minimal consistent subset. So, now we have less number of points with whom I have to find the distances. So, the complexity goes down. So, so, the new point we call a query point, which we want to classify. Okay. So, this leads to computational complexity. Okay. So, that is what happens. So, that is the first approach, we already studied it in the previous lecture. Okay. There is one more factor that actually determines this computational complexity, is that because it is not just how many points with which you are finding the distance, each distance computation takes more and more time if the dimension of these instances are high. So, if you want to find the distance between 2 points in 2 dimension x 1 y 1 and x 2 y 2, the computational time required would be less than computing the distance between 2 points in 3 dimension. Z 2, okay, finding in 3 dimension. Just because if you remember the formula for say the Euclidean distance, you have to do more square, more addition, more square root. So, it will, the more the dimension, the higher time it takes. So, now the thing is that can we sort of reduce this, not the number of training, not just the number of training points, but also the time required for each distance computation. Okay. So, researchers had proposed a number of data structures which will help us do this efficiently. Okay. So, these data structures are called search, high dimensional search data structure, or they are sometimes called geometric data structures, and they actually help us to compute this time in efficiently. So, the idea of all of these are following, that so I have these training instances and I have a query point and I have a value of k. So, that I want to find the k nearest neighbors. You can sort of assume that if you define a bounding box around your query with a proper dimension of the bounding box, proper region of the bounding box, then you can expect that all these KNN neighbors will lie inside this bounding box and not outside it. Okay, definitely. For example, here this cannot be KNN, this cannot be KN, this cannot be KN, this cannot be KNN. Okay. So, basically you sort of expect that all these k nearest neighbors will lie inside this bounding box. Okay. So, what advantage that gives us? The advantage we get from that is that now instead of finding distance to all these points, you find distance to only these points and sort them. That means you define a range, let me call this as a range box, a range box or a range rectangle. KNN will be among these points only. So, you have a reduction in computation. you are reducing the number of distance computation to only a subset. Okay. So, now, so basically what we do is the following. Before you have to do this KNN classification, you sort of break up your training set into boxes like this, break them up into boxes like this beforehand. Beforehand, you break them up your attribute space, so to say, or feature space, so to say, the set of instances into boxes. And when a new query point comes, you do two steps to find the nearest neighbor. First, you find out which box this query belongs to, Q belongs to. You find out which box this Q belongs to. Second, find distances to the points lying inside that box only. Okay, so, you find distances only to these boxes and then sort them and take the top k. Okay. So, that is the idea. So, let me tell you a data structure which does this. There is a data structure called the k dimensional tree, KD tree. Okay. Actually, you might have encountered this type of phenomena in another context. If you have done a database course, you must have known what is a index, specifically what is a B plus tree, for example, index. Okay. So, if you remember what a B plus tree does in database is that it if you want to find all records in a database having a certain key value, you make a hierarchical structure, tree like structure on the key values. Okay, where the leaves point to record pointers. And then when you get a key value, you sort of search through the tree till you reach a leaf. Okay. So, it is the same thing that I am doing here, but instead of finding a match with a single key, a equality query, we are doing a range query, whether a key value some point falls in some range. Okay. So, what we do is the following. We break up a space by something. So, for example, here, so I have two axes. So, the first split, the first node is on x axis. Okay. So, x less than 5, 1. So, all the points in this subtree will correspond to this, and all the points in this subtree will correspond to this. Okay. So, now among these points we split on y equal to 3. So, these points I split on this. Okay. So, these points I split on this, similarly these points may be y equal to 6 I split on this. So, you see when a new point comes, suppose I have a point okay. So, one query point x equal to 4, y equal to 5. So, something here 5.5 something here. Okay. So, what I do is that I just push down this x y through this tree and find out which leaf it belongs to, which box it belongs to. Okay, in this case maybe the B box. Okay. And then we look at other points in these neighbors and find the KNN among them, not the other. Okay, among them only. Okay. Now, one question is how do I decide on this tree structure? So, usually what people will do like this, there are many ways of constructing a KD tree. So, you know this is a index, this as I mentioned before that this is a kind of index search, a tree structured index, k dimensional tree structure index, because there are so many dimensions I am taking. Okay. So, how do I split? So, suppose I have a data distributed like this, say I have okay. I have a data distributed like this. I see along which x the variance of the data, the spread of the data is highest. Okay. So, in this case x has the higher spread than y. We take the median in that direction as my first field, 5 is the median, and then repeat this recursively for each of the subsets. So, for example, here draw it again. Okay. So, I get the root. Then what I do for each of these half, again I see. So, this half has more split in y than it has in x. Okay. So, what I would do is that among the childs y has more variance than x. Okay. So, you split on y on the mean value up these points only, not the other, only this up only and split. So, you get the second split. Okay. So, this way you continue and you get your tree, and then finally, you do a range search. When a query point comes, you put it into one of the, push it down the tree, put it into one of the box, find the neighbors among this box and find the k neighbors. All right. So, unlike earlier where directly on the training set I am doing, now I first index the training set, construct the tree, index the training set, construct the tree. Note that the finally the leaps, suppose if I stop here, the leaps will contain the set of training points, a set of among which I am finding the neighbor. So, all these training points will lie here, all these training points will lie here and so on. Okay. So, using that I can do it. There are many more data structures like KDT people have used, mainly for k nearest neighbor in really high dimensional data, people have used it, say a video file where you do a similar video search or image file. So, there people have used this. Okay. So, I do not go into many of them, maybe I will give you the reference material to study if you are interested. All right. So, to summarize, classifier, what it does? It approximates the base classifier. Stores only the training set. See, no construction, nothing is required. Stores only training set, nothing else, only stores. So, that is why it is sometimes called lazy learning also, sometimes instance based learning also. Okay. So, it is also actually many human reasoning. For example, a lawyer, when a judge gives a judgment, it looks at similar cases before, it just stores previous training example, it finds distance to the, it finds similarity with other cases on which judgment has been given previously and gives a similar judgment here. A doctor remembers all the previous patients, what were their disease, and when a new patient comes, it finds out its similarity, most similar cases seen before, and makes it same as the disease. Okay. So, this paradigm is a alternate name, it is called a case based reasoning. It is unlike logical reasoning. Logical reasoning we use some rule and deduct. In case based reasoning we use analogies, we use previous examples. Okay. So, that is the thing, it had KNN needs a choice of k, which is a open problem. It needs some distance measure, which is again domain dependent, and it has a problem of computational complexity. For which there are techniques like the condensed nearest neighbor and KDT to solve. Okay. So, that is the picture. There are many more extensions to the nearest neighbor. For example, you can do a nearest neighbor interpolation, you can do a nearest neighbor regression, all these things you can do, okay, not just classification. All right. So, in fact, we will show later, I will leave it to you as an exercise, any search problem, information retrieval problem. For example, in Google you are giving a query and finding all similar documents, similar web pages. So, that also can be seen as a k-nearest neighbor problem. So, it is up to you. I will give you some exercises where you will pose it as a nearest neighbor and define distances and other things and classify it, but it is a very powerful classification algorithm. Okay. So, I hope you have understood the basics of the KNN which I have taught. If you have any question, you can ask me through the forum or other mechanisms. Thank you.